Question number 1. It is related to the kinematics. The question says figure 1.1 shows part of the speed time graph for an athlete in a race. This is the speed time graph. Speed is here on the y-axis, time is written to be on the x-axis, and a portion of the graph is made over here. It is a straight line till the time 2 seconds. During the race, the acceleration of the athlete is uniform in the first 2 seconds. So in a speed time graph, we know that the gradient of the graph represents the acceleration of the moving object. So when the acceleration is uniform, we are expecting a straight line. And the reason of this is that straight lines have constant gradients. So gradients do not change in straight lines. During the race, the acceleration of the athlete is uniform. So the gradient should be constant, and it is represented using a straight line. In the first 2 seconds, state how the graph shows that the acceleration is uniform. So the graph is showing that the acceleration is uniform by a straight line. Since the gradient is not changing and it is a straight line, so the acceleration is shown to be uniform here. Next part. Determine the distance traveled by the athlete in the first 2 seconds. In a speed time graph, the distance is calculated by calculating the area under the graph. So if we try to find the area under this line, this would be representing the distance covered in first 2 seconds. Now we can see that the area under the line is a triangle, and there are 2 dimensions of the triangle which would be used for the area. This is the base, which is of 2 units length, and this would be the height of the triangle, which would be used to calculate the area. The value here is 9 meters per second, since it is in the mid of the 2 units, 8 and 10. So it is 9.0 for the height and 2 for the base. So I'm writing area under the graph is equal to the distance traveled, and it is 1 upon 2 times base, which is 2.0, and height 9. So the distance traveled is 9.0 meters, and I would be writing it in the answer space, 9.0 meters. The next part says during the rest of the race from 2 to 5.5 seconds, the acceleration of the athlete decreases. Now the acceleration is decreasing. At 5.5 seconds, the athlete reaches a maximum speed of 12 meters per second. From 5.5 to 8.0 seconds, the athlete travels at a speed of 12 meters per second. So the speed is not going to change for this interval, 5.5 to 8.0 meters. From 8 to 11 seconds, the athlete decelerates, finishing the race at a speed of 10 meter per second. Okay, now the graph from 2 seconds to 5.5 seconds would show an acceleration, and at 5.5 seconds, the athlete is going to reach the speed of 12 meters per second. Now, this would be the point where we would be showing 5.5 seconds time. The speed at 5.5 seconds would be 12 meters per second. And since the acceleration is decreasing, so we are going to make a curve over here. And that curve would show a decreasing acceleration. So this is the curve showing the decreasing acceleration, and at 5.5 seconds, we have reached the velocity or the speed of 5.12 meter per second. Now from 5.5 seconds to 8 seconds, the athlete is going to travel at a speed of 12 meters per second. So his speed is going to be constant over here. So from 5.5 to 8 seconds, the speed will not change its value from 12 meters per second. So this is the second portion. Now for the third portion, it says from 8 to 11 seconds, the athlete is going to decelerate, finishing the race at a speed of 10 meters per second. Now, the deceleration is constant or variable. It is not mentioned over here. So we can consider it to be a constant deceleration. And if we consider it to be a variable deceleration, then still the answer is going to be acceptable. For a constant deceleration, we are going to make a straight line. And for a variable deceleration, we are going to make a curve. So in either way, the answer would be correct, since this detail for the deceleration is not mentioned here. Now, from 8 to 11 seconds, we have to show the deceleration, and deceleration is to be shown in such a way that the final speed, the ending speed, would be 10 meters per second. So at 11 seconds, the athlete is going to move at a speed of 10. So I'm connecting it with a straight line. If you connect it with a curve, then still it is going to be correct answer for this question. Okay, on figure 1.1, complete the speed time graph for the times between 2 and 11 seconds. So we have already done it. It is a 3-mark question. So 1 mark would be awarded if this curve is drawn correctly. Then the second portion is the straight line portion where the speed is not going to change. And this is the third portion showing the constant deceleration. And this would earn us 3 marks. Question number 2, figure 2.1 shows the thinking distance and the braking distance for a car driven at 100 kilometers per hour. Okay, the car has old smooth tires. Now, thinking distance is the distance covered when the driver sees a hazard or something because of which he has to apply brakes, and till he starts to apply the brakes. So during this period, he would be processing, his mind would be processing and taking a decision that he has to apply a brake. So the distance covered between seeing a hazard and applying the brakes is called the thinking distance of a driver. Then the braking distance is the distance when the brakes were applied until the car came to a halt or it stopped. So when you apply brakes, the braking distance starts until the moving object stops. The distance covered is called the braking distance. Calculate the total stopping distance for the car. Stopping distance is the sum of these two distances, the thinking distance and the braking distance. When we add these two distances, this becomes the total stopping distance for any moving object. So we would be adding 21 and 75, and it gives us the value of 96 meters. So the stopping distance for this moving object is 96 meters here. The car is now fitted with new tires. So the tires have now been changed. At a speed greater than 100 kilometers, the total stopping distance is the same as in the previous part. Now, here the car was moving at a speed of 100 kilometers per hour, and with the newly fitted tires, the speed of greater than 100 kilometers per hour, the stopping distance remains the same. State and explain the effect that the increase in speed and the use of new tires. So these are the two factors. The speed has been increased and new tires are being used now have on the thinking distance. What would be the effect of these two factors on the thinking distance? The effect would be that it is going to increase. And why it is going to increase? Because speed is faster, although the time would remain the same. The time in which the driver is going to make a decision and apply the brakes, starts to apply the brakes, is going to remain the same. But the thing which is going to be important here is that since he was moving at a faster speed, so the distance covered is going to increase here. The next part, state and explain the effect that increase in speed and the new tires have on the braking distance. Now, the braking distance in this case is going to decrease, and the reason for this is that the newly fitted tires, the new tires, would have a larger friction. So we would say that force of friction would be larger. Old tires and the smooth tires do not offer much amount of resistance, and that is why the braking distance is lower in that case. But here we are going to experience larger force of friction, which would decrease the braking distance here. Next question, it is related to the topic of pressure and moments. The question says figure 3.1 shows part of a hydraulic press that is used to compress waste paper into a brick for burning. So this is a hydraulic press. We are going to apply a force on this handle. It is connected with a pivot, and a little before the pivot, a piston P is connected, which is going to receive this moment, and it is going to push this. Then this oil would carry the pressure to the other piston, and this is the second piston, piston Q, and above this piston the waste paper is present. So when the pressure is coming to this piston, it is going to press this waste paper, and in this way the waste paper would be converted into a brick for burning. Now the question says a force of 20 Newton is exerted downwards on the end of the handle. So we are applying a force of 20 Newton downwards on the end of this handle. Define the force on the handle creates a moment about the pivot. So this is the pivot. When we press this downward, there is a moment in the handle in the downward direction. Define the moment of a force. So moment is defined as the product of force and perpendicular distance between the pivot and the line of action of force. So moment is given by this formula, F multiplied by D, where D is a particular distance. It is the perpendicular distance between the pivot and the line of action of force. Explain why the force exerted on piston P is greater than the force exerted on the handle. Now the force exerted on the handle is 20 Newton, but the force exerted on this P is going to be greater than 20 Newton, and we have to explain the reason for this. Piston P is at a smaller distance from pivot than the point on the handle where the force was exerted. Now, when we exert a force at a larger distance from the pivot, the moment created would be the product of this force and this distance. The same moment would be transferred to this piston P. But since it is at a very smaller distance, so the force being applied on this piston is going to be much larger than 20 Newton because of having a smaller distance. So this is how the mechanism is used. So the moment created by the force on the handle is transferred to the piston P, and since the distance is smaller, the force exerted would be much larger. Next part. Explain how the hydraulic press enables a greater force to be exerted on piston Q than is exerted on piston P. On the piston P, we can see that the area of the piston is smaller, and on the piston Q, we can see that the area of the piston is larger. So whatever pressure is generated on this piston P by dividing the force with the area, the same pressure is transferred through the oil to the piston Q. And for this piston Q, since the area is larger, so for having the same amount of pressure as the answer, the force has to be larger as well. So for example, we created a pressure of 1 pascals over here such that the area was 20 and the force was 20. So 1 Pascal here would be created. For example, if the area is 40, then the force has to be 40 here. So the value of force is going to adjust in a way that the final answer should remain the same. The same pressure which was transferred from piston P through the oil and reached and acted on the piston Q, the same pressure is going to be the answer of this division. Since the area has increased, so the force would be increasing accordingly so that we get the same answer of the pressure over here. The first thing we would explain that piston Q would experience the same pressure as generated by piston P. This is the first point. And secondly, larger area of piston Q requires a larger force on piston Q for this pressure. So if we have to keep the pressure constant for a larger area, a larger force is needed. So these are the 2 points for a 2-mark answer here. In the next part, it says in moving the handle downwards, the 20 Newton force moves through a distance of 0.60 meters. So we are given with the amount of force and the distance it moved. A piston Q rises by 0.020 meters. The force exerted by piston Q on the paper is 400 newtons. Calculate the work done in moving the handle downwards. So work done is calculated by force multiplied by the distance. Force is 20 Newton for the handle, and the handle moved a distance of 0.60 meters. So when we multiply these two values, we get an answer of 12 joules. So the work done was equal to 12 joules here. Second part, the efficiency of the hydraulic press. Efficiency is calculated using the formula total work done input and useful work done or energy output multiplied by 100 so that we can give the answer in percentage. Now, the total work done input was the work done on the handle, and the total work done output was the work done by the piston Q. So it was 12 joules, and the output was 400 multiplied by 0.020. So this is 8 divided by 12, and it is going to be 2 upon 3 multiplied by 100. So it is going to be 66.6%, and in two significant figures we are going to write it 67%. So the efficiency of this setup is 67% over here. The question says two mirrors A and B are inclined at an angle of 60 degrees to each other. So this is the mirror A and this is the mirror B, and they are inclined at an angle of 60 degrees with each other. Light strikes mirror A at an angle of 30 degrees as shown in this figure. So a ray of light is coming and strikes the mirror, and the angle measured is 30 degrees, and it is being measured with the surface of the mirror. Now, in the first part, we are required to determine the angle of incidence at mirror A. Now, the angle of incidence would be measured using a normal, and normal is a line which is perpendicular to the surface at which the light is striking. So this is going to be the normal, and it is made as a dotted line. Secondly, we are going to measure this angle, the angle from the normal till the incident ray. And since we know that this total angle is of 90 degree, so the angle here is going to be 90 minus 30 equal to 60 degree. So the angle of incidence at A is going to be 60 degrees. Determine the angle of incidence at mirror B. Now, the light reflected from this surface, and it is striking the mirror B at an angle of 90 degree with the surface of the mirror B. So when we draw a normal over here, this is again going to be perpendicular to the surface of the mirror. The angle between this ray and the normal is going to be 0 degrees over here. So the answer for this part is going to be 0 degrees. Next, describe the path of the reflected ray after it leaves mirror B. Now, when the ray reaches mirror and strikes the mirror such that the angle of incidence was 0 degree, so according to the laws of reflection, it would be reflected back on the same path such that the angle of reflection is also going to be 0 degree. The laws of reflection would be followed here, and it would be reflected back at the same path. So I would be writing here, it would be reflected back along the original path or the initial path that it was following when it was coming towards mirror B. Next part says a plane mirror hanging on a wall is used to form the image of an object. State three characteristics of the image formed. So whenever the image is formed using a mirror, uh, there are some characteristics of the image. We have to write any three of them. First could be it is always virtual. Second, it is always upright. And third could be it is always laterally inverted. Similarly, it is at the same distance from the mirror as the object from the mirror, and it is of the same size as the object. So since we have to write any three, we could write these three as the characteristics of the mirror, of the image formed by the mirror. Okay, next question. It is related to electromagnetic waves. The question says the components of the electromagnetic spectrum have different uses. Microwaves are used in cooking, and ultraviolet rays are used in sterilization. Draw one line from each component of the spectrum to another suitable use for that component. Now, microwaves, they are also used for satellite televisions. Radio waves and microwaves are commonly used for communication systems also. And ultraviolet rays are used for sunbeds so that they can trap heat. The next part says figure 5.1 shows a microwave oven used to heat soup. The container for the soup is a glass bowl. Microwaves created inside the oven are reflected by the metal wall. So this oven has metal walls, and whatever the waves, microwaves are created, they are reflected back so that they are concentrated towards this pot or the bowl, and the soup is heated up. Explain why the choice of material for the container is important in microwave cooking. Microwave cooking. So the choice of material is important so that microwaves are not absorbed and not reflected, and they should refract. So when the refraction would happen, the microwaves would reach to the material or the substance which is to be heated or which is to be transferred with the heat. And if they are absorbed in the material or reflected by the material, then obviously the phenomena of the cooking or heating up cannot take place. So this is the material, the glass material which was used here, and it is a material which can refract the microwaves so that they can reach the soup and heat it up, and it itself should not absorb the microwaves in a large quantity so that heat is not wasted. Okay, the soup is mostly water. Microwaves are completely absorbed by a few centimeters of water. As a result, microwaves do not reach the center of the soup. So initially, whatever the material is present near the glass or near the surface, it completely absorbs microwaves, and microwaves itself or themselves are not able to reach the central portion of the soup. As a result, microwaves do not reach the center of the soup. The instructions suggest that after the microwave oven is turned off, the soup is not stirred, is left for some minutes so that the center becomes hot. So these are the two instructions. Number one, it is not to be stirred. And secondly, it should be left for some minutes so that the center also becomes hot. State the name of and describe each of the two processes by which thermal energy transfers throughout the soup after the microwave oven is turned off. So name of the first process. First process and the most effective process in the fluids through which the heat is transferred is convection. And the second process which can happen here is conduction. Now, what is the description of the convection? Convection happens when hot liquid rises and cold liquid falls and replaces it. So this is how the convection current is established in a fluid or in a liquid. Now the conduction happens when energy is passed from molecules to neighboring molecules through collisions. So when the molecules with high energy collide with their neighboring molecules, they transfer energy, and this process is called conduction. Since there are larger gaps in the fluids and liquids, and the molecules are not very tightly packed together like it happens in the solids, so the conduction is not very efficient in the fluids, but it still occurs, and the heat energy is transferred to the conduction also in the fluids. The next question, it is related to the practical uses of electricity. It says the clothes iron shown in figure is connected to the electrical mains. So this is how it is connected to electrical mains. The boxes in the left column below contain some electrical hazards. The boxes in the right column contain methods of protection from these hazards. For each hazard, draw one line to the appropriate method of protection. So electrical hazards are listed over here. The first one is worn insulation on the cable to the iron. So if the insulation is worn, it could be checked by a visual check, and it would be clearly seen by the person who is checking it. Loose live wire in the iron touches its metal case. So when the live wire is touching the metal case, there would be current in the body of the appliance, and it is protected by using the earth wire, so that this current should go to the earth or the ground and should not be causing electrocution. Cable becomes too hot because current is too high. Since the current is too high, so for from the protection of overcurrent, circuit breakers or fuses are used. So this hazard is protected by this method of protection. The next part, the power of the iron is 1200 watt. The cost of 1 kilowatt hour of electrical energy is 20 cents. Define the kilowatt hour. Kilowatt hour is the commercial unit of electrical energy, and it is defined as the electrical energy used by an appliance or a device of 1 kilowatt power when it is used for 1 hour. So if an appliance of 1000 watt or 1 kilowatt is used for 1 hour, then the electrical energy used would be equal to 1 kilowatt hour. The iron is on at full power for 20 minutes. Calculate the cost of running the iron for this time. So first of all, we are given with 20 minutes, and we are going to convert it into hours by dividing it with 60. So it becomes 1 upon 3 hours. The power rating for the iron is given, and it is 1200 watts. So it should be converted into kilowatts. So 1200 watts, and 1200 divided by 1000 would become kilowatts. So it is 1.2 kilowatts. Or we could also write it as 6 upon 5 kilowatts. Now, the cost of 1 kilowatt of electrical energy is given to be 20 cents. So this is the cost per unit. So I'm writing cost per kilowatt hour or per unit is 20 cents. Now, the cost of electrical energy is power in kilowatts, which is 6 upon 5, multiplied by the time in hours, which is 1 upon 3, multiplied by the cost per unit. And I'm also writing the formula here. Cost is equal to power in kilowatts multiplied by time in hours multiplied by cost per unit. So this is going to be equal to, so 8 cents. The cost is 8 cents. Radon 222 is an isotope of radon which undergoes a series of radioactive decays. Figure 7.1 is a diagram showing the proton number, atomic number, and nucleon number, mass number of nuclei involved in the series of decays. The point P represents a nucleus of radon 222. So it is here, radon 222. We can see that the nucleon number is 222 and the proton number is 86. Starting at P, a nucleus of radon 222 decays to Q, then from Q to R, and then from R to S, and then from S to T, and finally from T to U. State 2 points on figure 7.1 which represent the isotopes of the same element. So the isotopes are the ones which have same proton number but different nucleon number. So T and Q, they both have the proton number 84 but they have different nucleon number. Similarly, U and R, they have same proton number but different nucleon number. So we could write it as U and R. Different isotopes of the same element have different atomic compositions. State how the composition of their atoms is different. So there is only one difference, and it is they have different number of neutrons. Otherwise, the proton number and the number of electrons are same. A nucleus of radon 222 emits an alpha particle as it decays. The radioactive decay of a single nucleus is random. Explain what is meant by random radioactive decay of a nucleus. So randomness is that time when decay or emission of radiation would occur is not constant. Or we could also write the answer using the direction. The direction and the angle in which the decay occurs is not known. In nuclei notation, radon 222 is written like this. When a nucleus of radon emits an alpha particle, it decays to an isotope of polonium, PO. Complete the decay equation. So for the alpha, the details are it has a proton number of 2, and nucleon number of 4. For polonium, the proton number is going to decrease by 2, it would become 84, and the nucleon number is going to decrease by 4, so it would become 218. Now, the sum of nucleon numbers on the right hand side and on the left hand side should be equal. 222, 218 plus 4, 222. Similarly, proton numbers should be same, 86 and 84 plus 2, 86. State the name of the particle emitted by a nucleus of R decays to a nucleus of S. Now, R has a proton number of 82 and nucleon number of 214. S has the same nucleon number, but the proton number has increased by 1. So when a beta particle is emitted, this sort of change in the nucleus occurs. So the answer is beta particle. When beta particle is emitted, proton number increases by 1, but the nucleon number remains the same. Describe the change in the composition of a nucleus of R as it decays to the nucleus of S. S has 1 more proton and 1 less neutron, because a neutron is converted into a proton and electron when beta emission occurs, than nucleus of R. So this is the difference. S has a greater number of proton and 1 lesser number of neutron. Okay. Next question related to electricity. Figure 8.1 shows the circuit diagram of a temperature gauge. It contains an ammeter, a thermistor, a fixed resistor, R, and a battery. The current is measured at different temperatures and a graph of the result is shown. So in this graph, we can see that the temperature, when increases, the amount of current is also increasing, but they are not directly proportional. It is a curve which shows that they are related to each other directly, but they are not directly proportional. State how the resistance of the thermistor changes with the temperature and explain how figure 8.1 shows this. Number one, how the resistance of the thermistor changes with temperature. We would say that resistance decreases when temperature increases. This is the general behavior of a thermistor. Explain how the figure 8.2 shows this. The graph shows this. So it is evident that current is increasing when the temperature increases, which means that resistance is decreasing, therefore the current is increasing. Resistance and current are used for the measurement of temperature. State one other physical property that is used for measurement of temperature. So for example, we could use the volume for the measurement of temperature, the change in the volume. So volume of liquids or gases could be used to measure the temperature. A temperature scale involves the use of fixed points. State what is meant by the ice point. The temperature at which water freezes and converts into ice, or melts and converts from ice to liquid. The steam point. The temperature at which water boils, means it changes from liquid to gas, or it condenses and changes from steam to liquid water. At 80 degrees centigrade, the potential difference PD across the thermistor is 3.6 volts. State what is meant by the potential difference. The energy transferred per unit charge. The energy transferred per unit charge when passing through a component of the circuit. So whatever is the energy transferred from charge is taking place, that would be the potential difference of the component. The next part says calculate the resistance of the thermistor when the temperature is 80 degrees centigrade. Now, for this, we have to use this graph. And at 80 degrees centigrade, we can see that the current is 0.014 amperes. So the value of current is to be noted from the graph 0.014 amperes. And secondly, we were given with the information that at 80 degrees centigrade, the potential difference across the thermistor was 3.6 volts. So V is 3.6 volts. And now we have to find the value of the resistance. We would be using the formula of Ohm's law. V is equal to IR. R is V divided by current. Voltage is 3.6 and current is 0.014. So answer is 260 ohms. So the resistance of the thermistor at 80 is 260 ohms. The electromotive force EMF of the battery is 25 volts. Calculate the resistance of resistor R. Now we can see that it is a series circuit and 25 volts is the EMF of the battery. Similarly, 3.6 volts is the voltage across the thermistor, which shows that the voltage across the resistor would be, when we subtract 3.6 from 25, and it gives us a value of 21.4 volts. In a series circuit, the total voltage or the EMF is divided amongst the components. So there are only two components. If the thermistor voltage share is 3.6, then the remaining voltage would be the voltage share of the resistor. Similarly, it is a series circuit, so the current through all of the circuit is going to remain the same. And from the previous part, we know that the current was 0.014 amperes. So the same current is going to flow through the circuit. So I'm noting down the two values, that the voltage for the resistor R is 21.4 volts and the current is 0.014 amperes. So resistance would be voltage divided by current. Voltage is 21.4 and current is 0.014. So the answer is 15,000 ohms. Resistance of permanent resistor here is 15,000 ohms. The current scale on the ammeter is linear. Using values from figure 8.2, a student marks the scale on the ammeter with temperature values that correspond to the values of the current. The temperature is then read directly from the thermometer scale on the ammeter. State what is meant by a sensitive thermometer. A thermometer in which the quantity, like the volume of the liquid, changes a lot for a change of 1 degree centigrade. So if the quantity or the liquid or the volume is changing uh, considerably, and it is changing a lot for the temperature change, then the thermometer is called sensitive thermometer. State and explain at which temperatures this thermometer is most sensitive. When the temperature is going beyond 80, then the smaller change in temperatures is creating a larger change in the current. Similarly, when it was at 40 and the temperature was changing from 40 towards 60, the current was not increasing that much. So it means that it is more sensitive at higher temperatures, and the reason is because there is larger change in the current. So the region where it is showing the larger change in the current, that is where the temperature or the thermometer was more sensitive. The temperature gauge is used to measure the temperature of a room. Suggests why the temperature obtained using the gauge is slightly higher than the actual temperature of the room. The reason is there is some heat produced in the components of the circuit, like the thermistor or the resistor. So they are passing current and heat is being generated there also. So that is why the effect of that heat would also be indicated on the thermometer, and the reading shown by the thermometer would be a little larger than the actual temperature of the surroundings. It says figure 9.1 shows a simple relay used to switch a mains electric motor on and off. So we can see that this is the coil and it is connected to a battery and a switch. So when the current flows through the coil becomes a magnet, and when it magnetizes, it pulls the iron armature towards itself. When the iron armature moves towards the coil, the upper contacts get closed, and when they close, the circuit for the motor is completed and the motor is switched on. And similarly, when we break this circuit and we switch off and open the switch, then there is no current flowing through the circuit. And when there is no current flowing through the circuit, the coil demagnetizes. It does not pull this iron armature anymore. So the contacts again open. And with the open contacts, the motor is switched off. Now the first part says explain why the motor switches on when switch S is closed. We have to describe the mechanism why it switched on when the switch S was closed. So number one, current flows through the coil and the core is magnetized. So when it is magnetized, it attracts the iron armature. When iron armature moves towards the core, the contacts are closed. So this is how the motor is switched on. Again, when the current flows, the iron armature, uh, the coil, and this iron core is magnetized and it attracts the iron armature. When it moves towards the core, then the contacts get closed and the motor is switched on here. Explain why the core is made up of iron rather than steel. We know that steel is a permanent magnet and it is a hard magnetic material. So when we switch on the circuit, it would take time to switch on the motor, and when we close the switch, it would retain its magnetism and the motor would not get switched off quickly. So the motor stays switched on even when the switch S is closed. So that is why steel is not a good choice here. The next part is a student suggests that the motor can be turned on and off without a relay. He suggests connecting the mains to a simple switch in series with the motor. Suggests one reason why in some situations using the relay is better. So relay is better because the switch is connected to low voltages. And when we connect it directly with the motor, then it is connected to high voltage because the motor would be um, making a large current flow through the circuit. So that would affect the switch also, and it could melt and get short circuited and could be a cause of electrocution as well. Figure 9.2 shows the coil of a wire wrapped around a cardboard tube. There is no core. There is an electric current in the wire in the direction shown by the arrow. So this is the direction of the current in which the current is flowing. Now, on figure 9.2, draw the pattern of the magnetic field inside and around the coil. Mark the direction of this magnetic field also. On figure 9.2, mark the north pole of the coil. We know that the magnetic field of a coil is similar to the magnetic field of a bar magnet, and the north pole of the magnet is found using the right hand grip rule. So when we align the curl of the fingers with the flow of the current, the thumb is pointing to the right. So this one is going to be the north pole over here, and this would be the south pole. Now about making the diagram, I'm making three horizontal lines within the coil. So this would be the first line, which is going through the coil. This is the central line or the middle line, and this is the third line. So these lines should be parallel to each other and should remain straight when passing through the coil. Now after this, it would take a turn like this and would make a loop, and then it would return to the south pole. So this is how one loop is being made here. Similar loop could be made using this line. So this would be the direction for this loop, and this line should be continued straight because it is exactly at the center, and the arrows would show the direction of the magnetic field. So if we draw at least two loops and three lines within the coil, then the direction and the magnetic field, the pattern of the magnetic field is completely explained, and we have also marked the north pole over here. Okay, the supply of current to the coil is removed. The ends of the coil are now connected to a sensitive ammeter as shown in the figure. Now there is no current flowing through the coil and it is connected with a sensitive ammeter. Describe how a permanent magnet is used to produce a large reading on the ammeter. So we could use a permanent magnet here to produce current through this coil. And this would happen when the cutting of magnetic field lines would take place. that would induce an EMF in the coil. And since the circuit is complete, there is a complete closed loop or path for the current. So the current would start to flow. And when the current flows, there is a reading on this ammeter. So one way of doing it is that move a magnet towards or away from the coil and move it with a larger speed. So when it is moved and moved with a larger speed, a larger reading on the ammeter is produced. Explain why a current is produced. Because coil is cutting the magnetic field lines and an EMF is induced in the coil. So the current flows in the complete circuit. Circuit is also complete here. So the current is flowing. So this is a basic phenomena. When we take a bar magnet here, we move it towards the coil or away from the coil, the magnetic field lines coming towards the coil would get cut. And when it is cutting the magnetic field lines, EMF is induced. And because of the induction of EMF, current would flow through the coil. An oscilloscope is a device used to display waveforms. Inside the oscilloscope, a beam of electron is emitted from a metal filament by thermionic emission. The emitted electrons are accelerated away from the filament by a potential difference of 2000 volts. State what happens to the metal filament for thermionic emission to occur. So it happens when the filament gets heated, and because of having a higher temperature, electrons start to emit. Explain why the electrons accelerate away from the filament. They are attracted by the positive potential and repelled by the filament because it is at negative potential. So that is why they accelerate away from the filament. The charge on one electron is 1.6 into 10 raised to minus 19 coulombs. Calculate the maximum kinetic energy of one electron after it has been accelerated through 2000 volts. We know the formula that voltage is equal to work done upon charge, which shows that work done, which is the maximum kinetic energy, would be the product of voltage and the charge. So the voltage here is 2000 and the charge of one electron is 1.6 into 10 raised to minus 19. So the answer is 3.2 into 10 raised to minus 16 joules. So this is the kinetic energy gained by the electron, which is equal to the work done on the electron. Figure 10.1 is the trace on the screen of the oscilloscope. The settings on the oscilloscope are 10 milliseconds per division. So this one division on the x-axis is showing 10 milliseconds time and 3 volts per division for the y-axis. So for the y-axis, this one division is showing 3.0 volts. Okay. Calculate the amplitude of the trace shown in this figure. Now the amplitude is equal to two divisions. We can see whether it is on the positive side or on the negative side. So two divisions means there is a voltage of 6. So two divisions multiplied by 3.0 volts gives us 6.0 volts. This is the amplitude of the given signal. Okay, the next part is calculate the time for one oscillation, complete wavelength of the trace shown in this figure. So for example, if we start measuring from this point, then a wave would be completed on this point. So there are 1, 2, 3, and 4 divisions. Or if we measure from the crest, for example, from this crest till this crest, then again we can see that there are 4 divisions. And we know that one division is representing 10 milliseconds. So I'm writing 4 multiplied by 10 milliseconds, which gives us a time period of 40 milliseconds. In this time, one wave is completed. The trace shown in figure 10.1 is caused by a sound. The sound travels through the air to a microphone from the place that it is made. The microphone is connected to the oscilloscope, which displays the waveform shown. Sound is a type of wave. State which type. So we know that sound is a longitudinal wave. Describe the motion of the air molecules as the sound passes through the air to the microphone. Air molecules oscillate or vibrate back and forth parallel to the direction of propagation of waves, forming compressions and rarefactions. So this is how the sound is traveling from the source till the microphone. Describe and explain how the trace on the screen changes as the pitch of the sound becomes higher. Now, pitch is related to the frequency of the sound. So if pitch is increasing, means frequency is going to increase. And for the increased frequency, we are going to have a shorter wavelength. The setting on the oscilloscope are unchanged. The trace on the screen would change in such a way that more waves could be seen because frequency of the sound has increased. And since frequency is number of waves per unit time, so when the frequency is increasing, it means number of waves formed in a unit time are going to increase, and that is going to decrease the wavelength of the waves. A student investigates what happens when a diode is connected between the microphone and the oscilloscope. Figure 10.2 shows the circuit that he uses. So this is the diode which is connected. With the diode, the output from the microphone is an alternating current, and the trace is as shown in the figure 10.1 on page 18. Describe the action of the diode on the current from the microphone. So diode would only pass current in one direction. And when the current changes its direction, because it is an AC current, the diode would behave like a open switch. In reverse bias situation, it would not conduct any current. On the grid in figure 10.3, sketch the trace seen on the screen when the diode is used. So now the original trace is like this. It has a positive half cycle, then a negative half cycle, then another positive, negative, and positive half cycle. So when the diode is, for example, conducting current in one direction, only this current would be allowed to pass. And when the negative signal comes, the diode is not going to conduct. So the current would become zero. Then the positive half cycle, then zero, then the positive half cycle. This is how the conduction of current would take place. So I'm showing it here. The trace would be like this, then it would become zero. Again, there would be a positive cycle after this. After this, there would be again negative half cycle, which would not be allowed to pass through because of the diode. And this would be the final positive half cycle. So this is how the waveform is going to change. Only positive cycles would be allowed to pass through the diode. When the negative cycle comes, diode is not conducting, so the current has become zero. And again, a positive half cycle. For negative, it is zero. Again, a positive half cycle. This is the altered waveform of the given signal.